Hey everyone, welcome to another video. So in this video, we're going to go over the complex plane. So I went over this in the last video, but I want to go over this in a little bit of grave detail. Um, so here is what the complex plane looks like. I'll draw this in the first quadrant. So on the x-axis, this will be the real axis of a complex number z. And the y-axis, we'll label this as the imaginary axis, the imaginary component of z. And so a complex number, we can express this as a vector, right? So if I let a complex number z equal to a plus bi in the first quadrant, for example, so a vector has a magnitude in a direction. So the magnitude r, which is defined to be the modulus of z. So we label this as the modulus of z. That's how you read this. And this equals to the square root of a squared. Let me write this a little bit better. A squared plus b squared. Okay. Just uses the Pythagorean theorem as that we know and love, right? And then the other component of a vector is it has a direction. The direction meaning its angle. So it will have an angle that's spread with respect to the positive real axis, right? With respect to the positive real axis. And so to figure out theta, its angle, it is equal to the inverse tangent of y over x, okay? In future videos, we're going to let theta be called, theta is the argument of z, the argument of the complex number, and it's labeled as the arg of z, okay? Sometimes you'll see the notation capitalized or lowercase. If it's capitalized, they call this the principal argument. The principal argument. Since sine, cosine, and tangent are periodic, we want to have a principal cut. So the angle for the principal argument is in between minus pi and then pi. Okay, so they label that as the principal argument of a complex number. Okay, so that's for you to take note on in future videos. But I want to go over just real quick about properties of the complex conjugate. So the properties of the complex conjugate. Okay. Um, as you recall, if this is a complex number, the complex conjugate is denoted as z bar. So let me give out some more room. The complex conjugate is denoted as z bar, and all you have to do is change the sign in the middle. Okay, so that's how we compute the conjugate of a complex number. Okay, so and there's some interesting properties of the complex conjugate. If I take the modulus of z, it's equivalent to the modulus of the complex conjugate. Okay, so that's important. Also, the second property is that the length of the complex number squared, it's equal to z times z bar, z conjugate, okay? The third, uh, the length of z is equals to the square root of z times z conjugate, okay? So pretty useful properties for the complex conjugate. And and I'm gonna write out some more properties of the modulus. Of the modulus. Okay, so if I have two complex numbers, so if I let z1 equal to a plus bi, right, and then z2 is equal to another complex number, c plus di, then z1 times z2 in its modulus is equal to z1 times z2 times z2. And then the modulus of z1 divided by z2 is equal to length of z1 divided by the length of z2. Okay. And also, these are similar to the conjugates. So let me write out a couple more properties of the complex conjugate as well. If I were to take the conjugate of, actually, let me write this down here. So, if I were to take the product of two complex numbers and take its conjugate, okay, this equals to the product of the complex conjugates of the respective complex numbers, and then likewise with division. So if I take the if I take division of z1 over z2 and I take its complex conjugate, it's equivalent to taking the complex conjugates of z1 and z2 and dividing that number. Okay, so that's pretty useful properties for complex numbers. So geometrically, the geometric definition of, let's say, addition and subtraction. So I'm going to go over just the definition of how we would visualize geometrically the addition and subtraction of two complex numbers. So suppose that I define one complex number z1 in here, and let's say I have z2 as this complex number over here as a vector, okay? So this is the real part of z, and then this is the imaginary part of z, okay? So to define vector addition, well, it's the same idea as tip the tail, right? So if I want to figure out the vector z1 plus z2, all we have to do is take the vector z1 and attach the start of z1 to the end of z2. So it looks like this. You can also use the parallelogram law. So you can draw in a vector that's parallel to z1. That's in green here. And also we want to draw the vector that's parallel to z2, right? And then the vector z1 plus z2 would be this vector, right in the middle. So z1 plus z2, okay? So that'll be that vector. And then, so this is for addition. And then for subtraction, it's the same concept, right? So if I have this complex plane right here, real part of z, and this is the imaginary component of z. So if I have z1 over here, and then I have z2 over here, And I want to compute Z2 minus Z1, okay? Z2 minus Z1. So that is equivalent to writing out the vector addition Z2 plus minus Z1. If you remember back in Calc 2 or Calc 3 or maybe even pre-calculus, if you take the negative of a vector, you're switching its direction. So minus Z1 would be, it would have the same length, but it would go in the opposite direction. So this is minus Z1, and then we just perform the same vector addition, but we're using minus Z1 and we're still tacking on Z2. So we just draw in a vector that's perpendicular to Z2, right? And a vector that is that's close enough. And we'll draw another vector that's perpendicular to Z minus Z1. So it will be this vector here, right? And so the vector subtraction would look like this. So this will be this vector, Z2 minus Z1, okay? You can also scale this back and we can draw the tip to tail version of Z2 minus Z1, and these will be parallel, okay? So take the so tip the tail, right? So I hope that made sense. So Z2 minus Z1, those would be those vectors. So let's go over some examples, okay? Let's see. I want to make sure I keep track. Okay, yeah. So graph Z1, Z2, Z1 plus Z2, and Z1 minus Z2 when, excuse me, Z1 is equal to 4 plus 2i, Z2 is equal to negative 2 plus 5i. So I want you to draw these vectors out on graph paper or what have you. And then come back and see if you have the right answers. Okay, so I assume that you worked on this example. So I'm going to draw out the complex plane. All right, so this is our complex plane, our real part, our real axis. And this is the imaginary axis, okay? So Z1 was 4 plus 2i. So that'll be a vector in the first quadrant. So Z1, so 1, 2, 3, 4, 5, 6, 7, 8. I should label out these hash marks. I don't want to get too sloppy. Okay, so 4 plus 2i. So that would be this vector right here. So in the first quadrant, it said Z1, Z2 is minus 2 plus 5i. So that would be a vector in the second quadrant. Minus 2 plus 1, 2, 3, 4, 5. 5i. So right here is our second vector, Z2. Okay, so what we want is Z1 plus Z2 first. Okay, I'll highlight this in green. All right, so Z1 plus Z2. So we are at okay. So 2 up and then 4 across. So what we can do is draw a vector that is parallel to Z1. And we also can draw a vector that's parallel to Z2, starting at Z1. So we are at 1, 2, 3, 4, 5. 4, 5, 1, 2. Right, so this is a vector that's parallel to Z2. Okay, and this would be the vector addition. Okay, Z1 plus Z2, which of course is just combine like terms with Z1 and Z2. So in this case, it is 2 plus 7i. 2 plus 7i. Okay, well, that made sense. Next, we want Z1 minus Z2. So I am going to label this, oh, goodness gracious, this color. Okay, Z1 minus Z2. Okay, so we want to take the negative of Z2, right? So minus Z2 would be this vector. So 2 minus 5. 2 minus 5 would be its opposite, right? So 2 minus 5, that will be down here. So minus Z2, and then just use vector addition like last time, right? So we want a vector that is parallel to Z1. So up to shoot, okay. So it'll be this vector, and we want a vector that's parallel to minus Z2. Minus Z2. So just to make sure that we're orienting properly. And so this vector would be Z1 minus Z2. Z1 minus Z2. Okay. Z1 minus Z2. That would be this vector. So 4 minus negative 2, so that's 6. 6. 6 plus, I'm sorry, 6 minus 3i. 6 minus 3i. Okay. So that's the geometry in algebra of vector addition and subtraction. So hopefully that made sense. Okay, so let's go over some more examples. For these examples, let's see. I want to do right here. Okay. No, my yellow color is gone. So I want that color. Okay. So let's look at some more examples. Describe the set of points in the complex plane. Okay. We want the set of all points Z, for which 1 plus I times Z minus 1. The real component is 0. That's the first part. B, we want the points where Z minus I is equal to the modulus of Z minus 1. Okay. So so the trick here is you want to set Z equals to, let's say, X plus Y times I. Okay. And then you want to look at what that complex number looks like. And then you want to determine what the real part is. Okay. So pause the video and try to see what you came up with for these sets of complex numbers. So best of luck to you, okay? Okay, so I assume you had a go at it. And let's actually go over what the solutions are here. So if you let z equal to x plus iy, we can simplify this quantity in the parentheses as 1 plus I times x plus y times I minus 1. Okay, so we want to figure out the real component of this number. So we want to use the FOIL method and combine like terms, and we'll see what we get. So if we FOIL out the first term, it will have it would be x plus y times I plus x times I minus y minus 1. Okay. So what this means is if we gather all of the like terms, this would imply that the real component is x minus y minus 1, and our imaginary component would be just y plus x. Okay, so we want the points where the real component is 0, right? So this portion is the real component, right? So all we want to do is figure out points y and x such that x minus y minus 1 is 0. Do you know what that describes? This describes a line in 2D, right? 2 dimensions. So if we solve for y, we'll have y is equal to x minus 1, right? So it's a line at x equals at y equals x minus 1, right? Slope is 1 and y-intercept is 1. Okay, so hopefully that made sense. Okay, part B is so we want to look at complex numbers z, which the modulus of z minus I is equal to the modulus of z minus 1. So, okay, so if we let z equals to x plus y times I, we can rewrite this quantity as x plus y times I minus I. And this has to equal to x plus y times I minus 1. Okay, so so gather all the real and imaginary terms together, and we should get on the left-hand side x plus y minus 1 times I. And this has to equal to the modulus of x minus 1 plus y times I. Okay. So the modulus of a complex number, well, this equals to the square root of x squared plus y minus 1 squared. And that equals to the square root of x minus 1 squared plus y squared. Okay. All right. Then we can square both sides to eliminate the square root. And this equals to x squared plus y minus 1 squared. And this equals to x minus 1 squared plus y squared. Okay. And from here, it's just figuring out a relationship between x and y. So it's going to be an implicit equation. We're going to have x variables and y variables on one side of this equation here. So if we FOIL out this term and this term, what we will get is x squared plus y squared minus 2y plus 1. This has to equal to x squared minus 2x plus 1 plus y squared. Okay. Actually, we won't have an implicit equation. I was wrong. So, okay, that's a good thing. So things will cancel, thank goodness. The x squares will cancel along with the y squared numbers, right? They cancel too. And also the ones, they cancel. And what we are left with is y equals x. Wow, another line. Sweet. So the set of all points would be a line where y equals x. So hopefully that made sense. Let's see. And okay, let me organize my stuff here. All right, so the last thing I want to go over in this section, excuse me. So this theorem, I'll say theorem, will be useful in later chapters in this course. And that theorem is what's called the triangle inequality. Triangle inequality. Okay. And this is for complex numbers. So for complex numbers, there's similar theorems for there's similar triangle inequality theorems, but they will behave the same. Okay, especially for complex numbers. So let z1 equal to a complex number, a plus bi, and z2 is equal to c plus di, right? Then the first part of this inequality says the modulus of z1 plus z2 is less than or equal to the modulus of z1 plus the modulus of z2. The second part of this inequality is the modulus of z1 minus the modulus of z2 is less than or equal to the modulus of z1 minus z2. Okay, z1 minus z2. So I'll show you the sketch of this proof. Okay. All right. So if we want to show this relationship plus z2 is less than or equal to this quantity plus the length of z2 squared. Oops. Not squared. z1 plus z2, that's what I meant. Comma. It is sufficient to show, so if we square both sides, it's equivalent to showing this statement, okay? z1 plus z2 squared is less than or equal to this quantity plus the length of z2 squared. Okay. So here to go from to show this inequality, okay, we want to show that this inequality here is true. Okay, so and the way to do this, we're going to use the law of cosines. The law of cosines to do this. All right. Remember all good old law of cosines in pre-calculus? You thought that stuff went away, but you're dead wrong. Okay. So let's say that's Z1, the complex number, and let's suppose this here is Z2. Okay. The complex number as a vector is Z2. And so the vector addition, if I just go from tip to tail, here's Z2. That vector Z1 plus Z2 looks like this. Okay, so that's the vector Z1 plus Z2. And then this here would be Z2. Okay. It's right here, that's Z2. And then, so we're going to use, if I erase this portion, we're going to use this triangle we're going to use this triangle that's illustrated here to show the triangle inequality. Okay, so the law of cosines is the following. So if I have the angle in between Z1 and Z2 as theta, right? So the law of cosines is this. So the length of Z1 plus Z2 squared is equal to the length of Z1 squared plus the length of Z2 squared minus 2 times the length of Z1 times the length of Z2 times cosine of theta, right? So that's the law of cosines right here. Okay, so this right here is the law of cosines back in pre-calculus, right? Law of cosines. So, and then back in Calc 3, I don't know if you are able to recognize this. This quantity here, so if I let Z1 equal to A plus BI, and then Z2 is C plus DI, right? We can write this out as like a vector, right? The length of AB times the length of CD, right? Times cosine theta. This here is equivalent to the dot product of those two vectors, AB dot CD, the dot product. Okay. So really so this quantity is -2 times the dot product of these vectors, AB dot CD, right? Sorry, that's my dog. Where was I? Okay, so this, so this, okay, so this quantity would be -2 times AB plus CD. Okay, that's the dot product. Okay, but if you notice, this is the real portion. So going back to products of complex numbers, so if we had Z1 times Z2, right? A plus BI times C plus DI. The real component was AC minus BD, right? So that was Z1 times Z2. But if this were Z1 times Z2 conjugate, A plus BI times C minus DI, right? The real component would be AC plus BD. That's what we see here. That's what we see right here. Okay. So therefore, another way to write out this quantity is just saying minus 2 times the modulus of, I should say, the real part of Z1 times Z2 conjugate. Okay, times Z2 conjugate. Okay, so so this quantity therefore is equal to the length of Z1 squared plus the length of Z2 squared minus 2 times the real part of Z1 times Z2 conjugate. Okay, Z2 conjugate. Okay, and then also, if I look at this quantity, Z1 squared plus the length of Z2, I'm sorry, the length of Z1 plus the length of Z2 squared, well, that will equal to, if we FOIL out these two terms, the Z1 squared plus 2 times the length of Z1 times the length of Z2 squared, I'm sorry, times length of Z2 plus the length of Z2 squared. Okay. And we can also rewrite this as Z1 squared in modulus plus 2 times the modulus of Z1 times the modulus of Z2 conjugate, since the modulus of Z is equal to the modulus of its conjugate, plus the modulus of Z2 squared. Okay. We're almost there. We're almost there. So, if we look at, so this quantity in relation to this quantity, what we have is, oh, there's an important thing to mention. So note for any complex number Z, and I want you to think about this on your own, okay? The real part of Z, okay? So the length of the real part of Z is less than or equal to the length of Z. So, yeah, so I want you to think about this, for example, and the length of the imaginary component of Z is less than or equal to the length of Z. Okay? And I want you to think about this on your own. And this is in your textbook too. And explain why. Okay? So if Z is equal to A plus B, okay, right? Okay? So, but we're gonna just use this for just take my word for it. Right? Okay, so we're going to use this relationship to get to what we want to show, right? So the modulus of Z1 plus Z2 squared, well, we've already showed that this equals to the length of Z1 squared plus the modulus of Z2 squared minus 2 times the real portion of Z1 times Z2, I should say plus. Yeah, so this should be a plus. Sorry about that. So that should be a plus. Z2 conjugate. And this here is less than or equal to the length of Z1 squared plus the modulus of Z2 squared plus 2 times the modulus of Z1 times Z2 conjugate. Okay. All right. So, and then if we and if we FOIL expand out, or I should say factor out this quantity, this would equal to the length of Z1 squared. I'm sorry. The length of Z1 plus the length of Z2 squared. Okay, so this is what we wanted to show. Okay. So it's plus because we had to deal. So this here is a plus because we had to take the conjugate of Z2, right? And that resulted as a negative dot product. So yeah, so hopefully that made sense. So as an example, right here, okay. So for example, if I have this statement, if the length of Z is 2, then I want to show this statement. 6 plus 8i, that's less than or equal to 12. Okay, so pause the video. I want you to work on this example and we'll come back to it. Okay, so now you've looked at this example. Let's see how we can show this. Okay, so the first version of this triangle inequality says the length of Z plus 6 plus 8i. That is less than or equal to the length of Z plus the length of 6 plus 8i. Okay, and this equals to 2 plus the square root of 6 squared plus 8 squared. 36 plus 64. So 2 plus, so that's the square root of 100, so that's 10. So you get an upper bound of 12. Okay, so that's how you get you the upper bound. For the lower bound, we want to use the second version of this triangle inequality. The length of Z minus the length of 6 plus 8i in absolute value in modulus is less than or equal to, okay, the length of Z minus 6 plus 8i. Okay, so this would be our lower bound. Okay, hope that made sense. Lower bound. Okay, so let's solve for this piece here. So this lower bound, this would equal to 2 minus the square root of 36 plus 64. 6 squared plus 8 squared. So that is equal to the modulus of 2 minus 10. And that is equal to the absolute value minus 8, which is 8. Okay, so that's how you get the lower bound. And that is what we wanted to show. So I hope that made sense. Now to check for comprehension, I want you to work on these problems. Okay, so page 13. And I wrote them down for you to the practice. 3, 4, 14, 20, 22, 43. And then 44. Okay, so if you have questions, let me know in the comments. Thank you for watching, and I will see you all in the next video. Good luck.